So the lab to be performed this week is going to be thin layer chromatography, also known as TLC. And in this case we're going to use it to analyze some analgesic drugs. So before we get into the actual technique, let's evaluate what chromatography is. Well, if we break down that word, we get chroma, which stands for color, and then graphy for graph. Okay, so if we take a look at the picture on the left there, what we're trying to see, or where this ultimately came from, and where we get the name chromatography from, was that people noticed that when you took an individual organic dye and you put it on some solid stationary phase, and when a solvent moved through it, like water, we noticed that there were color rings. Okay, so the colors spread out, generating what could be referred to as a graph. Okay, all chromatography techniques are going to separate two or more compounds based on a partitioning between two standardized phases. There's two normal phases. Those phases are your stationary phase or your mobile phase. So in the case of the filter paper technique over here, what we're looking at as our stationary phase is the paper itself, or if we did it with clothes, a shirt or cloth. And the mobile phase in this case would be something like water. Okay? Water hits and causes our compounds to spread out, so it's a solvent. And all of these techniques work based on the assumption that different compounds will interact differently depending on what phase they prefer to interact with. That interaction is primarily based on intermolecular forces. So I know everybody's sick and tired of hearing about intermolecular forces, but this is all about intermolecular forces. Okay? All chemistry is about intermolecular forces, so we still have to make sure we understand and go back to those. There are several different types of chromatography that we could use. This semester we're going to take a look at gas chromatography, okay, and that's going to happen in a couple weeks. And what's going to happen there is we're going to separate our compounds based on the gas phase, so hence gas chromatography. We could also do liquid chromatography, and as that name suggests, we're looking at different liquids. Column chromatography, we would hope separates columns, but it doesn't really work like that. It's actually going to separate pretty much anything we want. In most cases, we're looking at separating different solids that have been put into solution. Paper chromatography, as we already discussed, and then we've got thin layer chromatography, which is our goal or our end result for today's lab. We're looking at a stationary phase, which happens to be a thin layer, hence thin layer chromatography, a thin layer of some absorbing material. Okay? In this case, our focus is going to be silica gel or aluminum. For today's experiment, we're really looking at just the silica gel. Last type of chromatography that you might actually see in the industry is high performance liquid chromatography, or HPLC. Okay? You'll probably see these acronyms tossed around all over the place. As far as thin layer chromatography goes, it's one of the more common ones. It's used pretty much every day in a synthetic organic lab because it gets a lot of useful information with a relatively short amount of time. Okay? We can use it to determine the number of compounds. So if we get an unknown mixture, we have no idea what's in it, we could run TLC to figure out how many different compounds are in it, because we can see how those compounds interact differently. If we know standards of what or how our compounds are supposed to move through the TLC, we can identify compounds in our mixture. Probably the most common thing used for TLC is to monitor the course of a reaction. During a reaction, we might expect our structures to change. Well, as the structure changes, the intermolecular forces change, which then means how each of those reactants and products interact with our thin layer chromatography. Our thin layer of silica changes as well, so we end up seeing some change in our results. We can also use it to analyze purity, and the last one we can use it for would be determining the conditions that we would need to use for column chromatography. So as we'd already stated, we've got two main phases when we're dealing with all chromatography. We've got a stationary phase and a mobile phase. When it comes to thin layer chromatography, and ultimately, as we'll see, column chromatography, our stationary phase is silica gel, and that's going to be the most important aspect of how we're going to see separations and how we're actually going to interpret TLC. So it's all coming back to that stationary phase. Okay? So if we're concerned about the stationary phase, it might be a good idea to look at it and see what intermolecular forces it has or what it could do. So we've got our two common ones here, silica and alumina. So we could go in and zoom in on those structures, or zoom in on the surface. So if we were a compound that was coming into this situation, coming in likely from the top onto our silica or our alumina. And if we're concerned about our intermolecular forces, it might be a good idea to evaluate what we might see if we were that compound dropping in on top of that silica. So what is on the surface? Well, we can go through and kind of highlight what's up there. We're looking at an awful lot of oxygens. In this case, we've got some hydrogens up there too. Okay. Well, what does that tell us? Well, we've got oxygen-hydrogen bond. Okay. What type of bond is an oxygen-hydrogen bond? That's right, it's a polar covalent bond. If we're concerned how that bond will translate into the forces, how can that molecule or that bond interact with a secondary molecule, we would then say dipole-dipole forces. We take that a step further once we found the dipole-dipole and say, do we have a hydrogen bound to oxygen or nitrogen? In this case, absolutely we do, which means the type of force that we would be seeing based on the drawing we've got here is hydrogen bonding. How strong of an interaction is that? Okay, it's one of our strongest interactions, one of our strongest forces, which would suggest that our stationary phase is quite polar. Okay. So before we continue on, we're going to take a second look back at the identity of our silica and our alumina. So we've got our names up here at the top, our silica and our alumina here. We've also very kindly drawn out the formula for each of these. Okay, and you'll notice in that formula, you don't see any hydrogens. Okay. Our compounds happen to be extremely polar, and in the presence of water, even water in the atmosphere, hydrogens can and will attach to some of those oxygens. Okay? But more than likely, okay, or in our situations in theory, those hydrogens would not be there. Okay, so we could go through and cross those hydrogens out. And the reason we want to go through and do this is we want to take a closer look at what possibilities or what things we need to be considering when looking at these bonds. So I'm going to cross this last hydrogen out and then draw the bond on over here. So I want to look at that bond. Okay? And in that bond, we've got some electrons. And if I'm deciding to go through and remove the hydrogen in every single one of these other cases, I need to know where the electrons in that bond go. Okay, so where should they go when that hydrogen is removed? Should it go with the hydrogen or should it stay with the oxygen? Okay, well, we'd figure that out by looking at the electronegativities. Oxygen is much more electronegative than hydrogen, meaning those electrons would probably stay with our oxygen. Okay? So that if we then look at oxygen as far as the Lewis structure goes, we could go through and say that we'd actually be looking at 3 lone pairs around every single oxygen. Well, oxygen with 3 lone pairs happens to be charged. Okay, in this case we're looking at a negative charge. So before, where we said our intermolecular force was a dipole-dipole force or then hydrogen bonding, we don't have that hydrogen anymore, so we can't be hydrogen bonding. So we need to now evaluate what our strongest intermolecular force would be. Okay, so we go through and identify our bonds. And in this case, okay, we should have a giant red flag, okay, raised here with that negative charge. That negative charge is an anion or an ion. Okay, so the intermolecular force that we're looking at is an ionic force or electrostatic. Why is that important to evaluate? What does that mean about our intermolecular forces? Okay, we've got a very strong force. What does that mean about our stationary phase? Our stationary phase is very, very polar. Okay, we're going to see why that's relevant as soon as we bring in bring in our molecules. So let's take a look now just at our silica. So we'll attempt to kind of simplify things here. And we're going to draw on 2 compounds. Okay, we're going to look at benzoic acid. So we'll draw this guy on here. So we've got the benzene ring followed by our acid functional group. Okay, and I've always said that we need to draw on our lone pairs, so let me go ahead and do that so we can see them all. There are lone pairs on our oxygen. So we've got benzoic acid, and I'm also going to draw a second structure. This structure we'll draw out as naphthalene. Okay. And now what I'm concerned about is that how these two structures can interact with our stationary phase. So what we're concerned about is this attractive force. Okay, what's happening in red here? So let's take a look at our benzoic acid first. Well, we already said our silica was ionic. What intermolecular force would our benzoic acid have? Well, we'd go through and find the bond that we're particularly concerned about, okay, which in this case would be the one between the oxygen and the hydrogen. That's a polar covalent bond, which means dipole-dipole forces, which means hydrogen bonding because we've got an oxygen or a hydrogen bound to an oxygen. So we're looking at a hydrogen bonding interaction, okay, coming from our benzoic acid. So if we now had to evaluate, say, the strength of our intermolecular force between those compounds, okay, we've got ionic, which is a very polar, strong interaction, and we've got hydrogen bonding, which is also a very polar, strong interaction, which would suggest that the intermolecular force between those should be a very strong polar interaction. So we're looking at a strong force. We'll address that force in a little bit. If we now shift over to our other molecule, naphthalene, we still have our ionic force coming from our silica, or our stationary phase. We want to evaluate now the intermolecular forces possible for naphthalene. So for naphthalene, we'll go through and look at all the bonds. We've got carbon to carbon, which by definition has to be covalent, because it's the same atom. There's no difference in electronegativity. And then we also have carbon to hydrogen, okay, which is easy to forget because we've got implied hydrogens all the way around there. Okay. We've also classified those as covalent, which means the strongest force that naphthalene could ever put out is going to end up being, that's right, London dispersion forces. Okay. Or we could abbreviate LDF, right? So what does that mean? So now let's take a look at our intermolecular force. Okay, the attraction between these two molecules. Okay, are those similar forces or dissimilar? Okay, they're really, really dissimilar. And if we're going to look at the strength of that interaction, we could call that weak. Okay, the London dispersion structure does not want to interact with our ionic structure. We're looking at a very, very weak interaction. So why is any of that relevant? Well, so far, okay, what we have to remember is we go back to what TLC functioned on, or chromatography functioned on. It was looking at a partitioning between two phases, a stationary phase and a mobile phase. Well, we've looked at our stationary phase, okay, so we put our compounds onto it, and now they're stuck. Okay, they aren't going to move. Okay, the only way they can move is we somehow bring a mobile phase along. Okay, and that's our second phase when we're looking at TLC. And what's going to happen is we're going to get our compound near some solvent, and the solvent's going to wash over our silica surface and push everything with the exact same amount of force. So what does that mean if we go back to our compounds now? And I come along and I push benzoic acid. Okay, and I push naphthalene with the exact same force. Which one would we expect to travel further? Okay, the naphthalene travels further. Why? Because it's not attached. Okay, it's not stuck to our stationary phase like our benzoic acid is. Okay, this one's pretty much frozen to the surface. Okay, which means if I come along and push the benzoic acid, it doesn't move, whereas our naphthalene does move. Okay, that is the summary of all the theory behind this. Okay, so what we can do is now put this all into words. Our stationary phase is what's going to grab our compounds, and ultimately it's going to grab our polar compounds and hold them tighter. Our mobile phase is going to move across our stationary phase and just push everything, again, same force, and it's going to move through our stationary phase via capillary action. Okay? Depending on how our compound is attracted to the stationary phase, it's going to travel a slightly different distance than, say, another compound. The more polar our compound, they're going to interact more strongly with the stationary phase, which would mean they wouldn't move very much. So we get they move less up the TLC plate. If it's a nonpolar compound, it's going to interact less strongly with our stationary phase, which means it moves further up the plate. Okay? It's now part of the mobile phase, if we were. Okay? So what does this mean as far as our mixtures go, or what we can look at? So if we evaluate, in this case, it's kind of like a stop motion. We'll look at a TLC plate, which happens to be nice and rectangular. We're going to put our compound on it, which in this case is purple. Okay, that's our spot down at the bottom. Okay, and we're going to then put it into a solvent mixture. So we would drop this TLC plate into a liquid that would kind of be in here. The liquid's going to rise up through the plate via capillary action, and as it moves up, it's going to wash over our compounds and cause our compounds to move. So if we then compare to what happens as we continue in time. So as the solvent continues to move, now it's further up. Okay, it's washed across our compounds, and we notice that what was one spot over here has now separated into two separate things. Okay, why did it separate into two separate things? Well, there was two separate things there. Okay, and we see two independent spots because the intermolecular forces for compound A are different from that from compound B. Okay, and that's where our separation is coming from. We can continue to let our plate run until our solvent gets much closer to the top, and we see now a much larger separation between our two compounds. Okay, so can we come up with any information about the relationship between these two? Well, what's special about compound A, or component A? How far did it travel? Not really a lot, which means it stuck, which means it was part of the stationary phase. Okay, well, if it's part of the stationary phase, what can we say about the polarity of component A? It ends up being very polar. So component A is more polar than component B. Okay, well, what does that mean about B? That means component B, actually we can go stick with that, is more non-polar. Okay, so we found some information out just by running our TLC plate. We've learned a little bit of information about our compounds. Okay, some students might ask, well, why did we wait so long before we took it out and evaluated it? You notice that we had a second plate in here, and we continued to wait until we had a secondary situation here. Why did we wait that much longer? Well, most of your compounds are not red and blue. Okay? Most of them are colorless or white. So on the TLC plate, you won't be able to see them. Okay? So we would have to let it run for as long as we possibly could, maximizing that separation so that we can see our components. Because if we didn't wait very long at all, let's say we only let our solvent run up to, say, down in here, which in our first case, would we see any separation? Well, no, we didn't give our compounds enough time to partition between our two phases. Okay, so we want to maximize that partition time within reason. Okay, we could build a 1,000-foot plate every single time, and we would see great separation. It would just take years for that plate to run. So we're usually running with something that's in the probably 4-inch range. Okay. So as a summary here, we would expect component A to be more polar and component B to be less polar. Okay, so what is this going to end up looking like? Well, your TLC plate is this white thing in front, this little white rectangle here, okay, which is actually on its side right now. So the white portion of that is where your silica is, and then depending on how much money we actually have, The back of it, or the solid surface that holds our silica, could be anything from glass, the ideal situation, to aluminum, which is the cheap situation. We have the cheap situation. So make sure when you're running your TLC plate that you're putting your compound on the silica side, which means the white side. Don't try and put your compound on the aluminum side because there's nothing to separate there. Okay? So what you're going to end up doing is getting your compounds put onto your TLC plate, so you can mark where you'll put your compounds, spot your compounds onto it, and then you can go ahead and put it into your wide mouth bottle, which is this guy. Okay? And you'll have a little bit of solvent at the bottom of that. You'll put your plate in vertically. You'll cap it. The solvent will rise up through the plate via capillary action, allowing our spots to change or move different distances, and we'd end up with our final plate. Okay? Depending on who trains you, you might use a piece of filter paper in your TLC plate or in your TLC jar as well. That's up to your TA and you. So you can read more about the filter paper or talk with your TA to decide if you want to use that. While the TLC plate is actually running, if we take a look at that plate now in the during situation, you'll notice first off there's colors there. So this plate was nice because we see colors, we can see our separate spots. So if we really wanted to, we could go through and say, okay, let's take a look at this pink spot, which you now can't see, so let's try that again. We could look at the pink spot that's fairly low. We can look at a pink spot that's fairly high. Okay, would those two spots be the same compound? Okay, no, why not? They traveled different distances, which means their polarity was different. If their polarity is different, they're also likely different compounds. Well, how about that pink spot, our first one, versus, say, this spot right here in the middle, the blue spot? Could those be the same compound? Right? The natural response is going to be no, because they travel different distances. There's an easier answer. What's that easier answer? Pink versus blue. The colors are different. So we can make physical observations of our spots as well. It's not just how far they traveled. The other thing that I want to draw your attention to in this case, as I draw through our structure here, is the solvent front. So as our solvent is rising up through it, we can see our TLC plate get wet. Okay? And we've got that barrier between the dry and the wet side of the TLC plate, or wheat. Let's try that again. Or our wet side of our TLC plate. Okay? You can see that only while it's running, because more solvent is replacing it and keeping it wet. As soon as you open up that jar and take your TLC plate out, there's nothing to replenish it, and it ends up drying out. Okay? The solvent evaporates off, which means as soon as you decide your reaction's done and you decide to unscrew your cap, you'll pull out your TLC plate and you will immediately mark. Okay? And it is, and it is an immediate thing, because if you decide to wait, you're going to end up losing it. You would mark right along where our solvent front was. We said, okay, there's the solvent front. And we're going to talk about why that solvent front is so important here. So we take our plate out, and we've got our solvent front marked. But remember, we said that most of the compounds are colorless, so you wouldn't see any colors. So we need to come up with some visualization technique. And we're going to use two methods in lab this week. We're going to use ultraviolet light and iodine vapors. In the case of the ultraviolet light, most compounds don't fluoresce. So when you do blacklight parties or anything like that, you can see all the bright colors and everything. Oh, how trippy and cool. Okay, well, that doesn't quite work for us. Okay, so what we're going to do instead is the TLC plate that we're actually using has fluorescent dye embedded in it already. So when you shine the UV light over the top, that is going to glow kind of this distinct weird yellow green color. Okay, where your compounds are, however, the compounds are going to absorb that UV light instead of the plate. Well, if the plate never gets the UV light, then it can't fluoresce. And so what you end up seeing, as is kind of shown here, is dark spots on your TLC plate. So in the case of this TLC plate, it had 3 compounds in it because we saw 3 separate spots. Okay. The other technique we'll use is iodine vapors. So in the case of the iodine vapors, we'll have containers in the back of the lab that have iodine crystals in the bottom of that. Okay. You'll drop your TLC plate inside that and cap it. Please keep these in the hoods. There are some people that are allergic to iodine and it's not a particularly pleasant thing to experience. So go ahead and make sure you keep those things capped. You'll leave the plates in there for a couple minutes and then you'll come back and look at them, and what you'll find is that your TLC plate will have changed color. Some compounds will react with the iodine, leaving behind a brown stain. That brown stain will disappear eventually. So as soon as you take it out of the iodine chamber, mark your spot immediately so you can see it. And then just so that you're aware, there are other different techniques to visualize. We don't have to worry about those. There's a few of them listed there at the bottom. Very last thing that we really need to evaluate before we can kind of let you go is looking at the RF value, or the retention factor. Okay? If we look at an individual plate, we could go through and say, yes, we've got, say, in this first plate over here, we spotted 3 different things, and you can see those spots down at the baseline. Okay? And we can see that we've got 3 different components. Okay? What if we ran a second plate? Okay, say like the one over here. How would we be able to compare across? Well, we could say brown versus brown, but then do you think this compound and this compound are the same? I mean, they don't look like they traveled the same distance. To me, this one looks like it traveled a lot further. Okay. Well, what if we ended up using a really, really small plate? Okay. Is that going to be, if we tried to then even pick this same compound, we would expect it to travel, say, this distance. Well, that distance would put it somewhere off the plate, so that doesn't make any sense. So what we're going to do, instead of looking at just the sheer distance, is create a standardization, or a percentage. Okay? Something that will be consistent regardless of who runs the TLC or who does the plate. And to do that, what we're going to look at is compare the distance that your spot travels, or the distance your compound traveled, and we're going to compare that to the distance your solvent travels. Okay, we have to be very, very particular with that, which is why I said that you needed to mark your solvent front, because if your solvent front's not marked, you don't know how far the solvent traveled. Okay, so we need those 2 pieces of information, and we're going to set that up as a ratio. It'll be our spot distance over our solvent. Okay, well, the solvent, nothing can travel further than the solvent, so what's the absolute maximum value we could get for an RF value? Yeah, it would be 100%, or 1. Okay, all of your values are going to be less than 1. So to go through and calculate, we've got a second plate here with actual numbers. When you go through and do your experiment, you should have very similar calculation sections set up. So you'll go through, measure the distance that your solvent traveled, and the distance your spot traveled, and divide the spot by the solvent. Show those calculations in your lab report. Part of this experiment is to identify what your unknown sample is. So in this case, we've got 4 standards. Okay, so we've got A, B, C, and D as our standard compounds. So we ran those, and we also ran the unknown. And our job is to figure out what compounds are in the unknown. So what we'll end up doing is comparing our RF values. And if we take a look between these two, the unknown has a spot that seems to match the RF value for compound C. So we would say C is in the unknown. We can't leave it there because we also notice there's another spot in the unknown that happens to match the distance that compound B traveled. So we would say our unknown has compound B and C in it. We'd have to go through, show all the calculations for that, make sure that we can prove it. Okay. So some random facts about RF values. Your possible ranges are going to be anywhere from 0, the spot didn't travel at all, to 1, where it traveled as far as it could with the solvent. Okay? We can use the RF values to aid in understanding what our unknown is, so on identification. We have to compare back to a standard. That said, if they have the same RF value, if you get two spots that have the exact same RF value, they might be identical, but it's not a guarantee. Okay? TLC doesn't guarantee things, it only kind of gives you evidence suggesting. One thing that it does do for you is if it has a different RF value, if your two compounds have different RF values, those are absolutely not identical. So TLC gives you confirmation of the negative, just not quite as much on the positive. Okay? And the main reason being is that your RF value is only a constant given several variables are also held constant. So if we change the solvent, we change how our compound moves. If we change the adsorbent, our stationary phase, we also change how our compound moves. If the thickness of our adsorbent changes, so for instance, if we have a lot of silica versus very little, our compound's also going to change its speed through the TLC plate. The amount of material spotted on the plate can affect things as well. And lastly, we could also see effects based on temperature. Okay? And that's just a partial list of things that can mess with it. So when it comes to the analysis with TLC, we have to be very, very careful about concluding a positive value. We can really only guarantee the negative result, that it is not something else. Last thing we'll do, just take a look at TLC analysis in a nutshell. You'll run your standards, so in this case A and B, and you'd also run your unknown. Most TLC plates, based on the sizes and situations that we've got, you're not going to be able to put more than probably 4 spots or 4 independent compounds on an individual plate. Okay, we can really only fit, say, 3 things on there, maybe 4. If you start to put more things on there, instead of seeing a nice neat plate like this, what you might see instead would be a whole bunch of spots all over the place, and it becomes very difficult to tell what compound belonged in which lane, and you lose the analysis and you've got to restart your experiment. Okay, so you need to be careful with that. And before we send you off with those final words, I do want to do a brief mention about solvent effects. Okay, so if we took a look at a TLC plate and we said that we had compound A, compound B. Okay. We said, okay, fine, I don't like how far those spots traveled. Okay, I want them to travel less. Okay, what could I do to get those spots to travel less? Okay, you're right, we could change the polarity of the compound, but then we're evaluating a different compound, so that doesn't work. Our stationary phase stays the same regardless, so we can't change the stationary phase either. So yeah, that really only leaves our mobile phase. So what we can do is change our mobile phase. Okay, well, our compounds traveled a further distance because our solvent pushed harder. Okay, well, what did our solvent have to do? Why was it pushing harder? It's pushing harder because it was polar. Okay, it broke the intermolecular forces holding our compounds to the stationary phase, so it was a more polar solvent. If I want my compounds to travel less, what do I need to do? That's right, what I'm going to end up doing is making my solvent more nonpolar, so that if I run the same plate, I can expect my compounds to travel a little bit less. Okay, now here comes the fun question. Which is compound A, which is compound B? Okay, well, let's think back to what happened. B went further because it was nonpolar, period. Okay? If we change the polarity of the solvent, does that change the polarity of B? No. It only changes the polarity of the solvent, which means B would still be expected to travel the furthest. Changing the solvent has no effect on the order of our compounds. Okay, so let's kind of summarize this because this is a complex subject here. If we look at our compounds, a more polar compound has what kind of an RF? Whoops, let's try that again. Let's get that descriptor in there. Okay, the more polar the compound, what happens? Okay, that's right. We have a smaller RF. Why smaller? It traveled less. Okay, if it travels less, and when we compare that ratio, we end up with a smaller RF. But what happens if we now take a more polar solvent? Okay, so we're comparing something else. What happens to our RF values? Okay, and this is where it's kind of counterintuitive. Our RF is only based on the compound, not based on the solvent. Okay, so our compound RF ends up becoming, that's right, it becomes bigger. Okay, or larger. Why? Because our spots can now move further, because we've increased the polarity of the solvent. We're increasing the push. Our solvent is merely a pusher. The more polar our solvent, the harder it pushes. Okay, the more polar the compound, the tighter it holds to the stationary phase. Okay, so we're not separating our solvent. Our solvent is there, is always, always, always pushing, always, always, always washing over. Okay, so you got to make sure you keep those two things separated and away from each other. Yes, I know it's confusing, but make sure you treat them differently. Okay. Last thing that I'll leave you with, remember that these slides are posted to Blackboard, so you can take a look at these. These are all going to be important pieces of information that you should not do when running your TLC plate. Okay. For instance, if your hands touch the TLC surface, okay, you've got organic materials all over your hand, and you're made out of organic materials, right? So if you touch the surface with your hands, you're now contaminating the top of the plate with organic materials. It's going to mess up your plate. It's going to make it a big mess. You aren't going to be able to figure things out. Okay, so please read over that. If you need to pause the video and just look at it on the video, that's fine. Otherwise, you can find the slides through our website. Thanks for listening, and good luck in lab.